So what we have seen up until now, so we have started what we call rounding. Okay. So we have started rounding up until now. So what all things we have learned to round is that the basic primitive that we started with was like based on this what do you call extreme point rounding, right? Extreme point rounding, right? Which led us to what we call iterative rounding. Okay, so there's a whole book written on iterative rounding, and there are who are taking who needs grades? 4 of you need grades. Okay, I will get that. Okay, so then we move to this, what is it called? Rotate and round. Okay, and then using that we did bipartite matching. Okay, and then we also did, I think, 4/3 approximation or some approximation for 3 set packing. What was that? D set pack, 3 set packing we did, right? Okay, 3 set packing. Okay, what was the approximation ratio? One
7/3.
7/3, right? Yeah. And then from bipartite, then we use the idea from bipartite matching to gap problem, right? And then we said that, okay, this idea of this rotate and round is actually, so what was the basic idea of rotate and round? That, hey, for several problems, you gave me a fractional solution, okay, in poly time. I can convert this into an integral solution, okay, with no loss, right? So this was the main theme which was in this rotate and round thing. We say that this rotate and round thing is quite general and it can be done also for variety of convex kind of programming, and then we learned Pipez rounding, okay. And we applied this Pipez rounding to design 1 minus 1 by f to the power f approximation for max coverage on instances with frequency bound f. Okay, so this is what we have learned. Okay, so now today we will do what is like normal deterministic rounding. Okay, so today we will do what we call normal deterministic rounding. Okay, and we will pick up our favorite problem. Okay, and so if you notice that throughout this course we have done a couple of things quite frequently. One was this facility location. Okay, so what was the facility location problem? So in the facility location problem, we are given some set of facilities, set of customers, and for each I in f, I have some facility cost. Okay, and then there was a function, distance function from facility to customer, right? And what is the property? That if a customer is served by facility I, then for some I and j, we mapped it to some real di comma j. Okay, is that fine? And so we saw that if the facility location, if the distance function does not satisfy any constraint, then for this we gave order log c, what do you call, approximation ratio, right? But if you remember, we also gave a factor to approximation using greedy, right? And its variant, I think we did k median, for which we gave local search. So you can also do for facility location a local search. Today I will just give you for a metric version. What I will give you for metric version, a constant factor approximation, another constant factor approximation. So generally, the way we use vertex cover in lot of codes as our germane or our seed problem. For me, facility location, k-median and set cover are the three basic problems that will try to use our all methods and technology that we have learned across. So today we will do facility location, and what facility location? We have been, it satisfies the triangle inequality. Okay. So what is the meaning of triangle inequality here? Do you remember? Okay. So imagine that I have a bipartite graph F and some customer C, and some I have I and J, and let's say customer X, or rather let's say we will denote, okay, I1, I2 and J1 and J2, and I want to go to from J2 to I1. Okay. So then we are basically saying the distance from I1 to J2, right? If this facility serve this is less than equal to, first let's look at the distance from I1 to J1 plus distance from I2 to J1, okay, plus distance from I2 to J2. Okay. So this is what I mean by triangle inequality in the context of facility location. Okay. So this is fine. Is the question clear to all of you? We have, it's like this is not the first time we are talking about this problem. Okay. All good? Because there is no distance defined between two facilities. Okay. Okay. So I mean, anyway, this is the formalism that people have used in the literature. And now, so and what is our objective function here, right? And what is our objective function? Our objective function is to minimize what? Okay. Like our objective function is that minimize what? Minimize. So basically, we are deciding which facility to open, okay, which facility to open, okay. So basically I want to X subset of F to guess, okay, and there is no cardinality constraint. The moment I have a row, then I have a function from C to X, which tells us a particular customer is served by which facility in this, and that is the whichever is the minimum distance. So this is fixed, right? Minimum distance to a customer J to a facility in X. Okay. So this is what the sigma function is. So what was the cost of this? So cost of X, right? So cost of X is summation, okay, I in X Fi. So cost for opening this facility plus for all J in C, right, distance from sigma of J comma J. This is it. So what is my goal? I have to find X whose cost of X is minimized. Okay. So that is my goal. So this is the classical what you call facility location problem, and for this we already have seen with greedy a factor 2 approximation, but today we would like to see an approximation with respect to using LP. So first of all, how will you formulate an LP for this? First of all, how will you formulate ILP for this? For each facility we have a variable, okay, excellent. For each facility we have a variable, say yi, I in F, okay. So Definitely we are not going to minimize yi, right? That is not what it will tell us, right? Because that is not the cost function is, right? So minimize what? Okay. So minimize, okay, so let's write it down. Minimize summation yi I in f plus what? Huh? Oh, right, you all are. Right? J in customer huh? For what? To say what? Okay.
Client I is assigned to cluster facility J.
Okay. So all of you are saying that I also need a variable xij, which means j has been assigned. J has been assigned. J has been assigned to facility I. Okay. So now what should I write here? What should I write here? So how do I write this here? Like for every say, so like this is what? So now suppose I have run this. So what should I do here? So for each j in C, I in F, xij. Is that what you are saying? Times distance from I comma j. Is that correct? Okay, so let me just so that it is. So xij has been assigned. So now just for I am just moving it here, nothing more. Summation yi times fi, I in facility plus what should I write? J in C, summation over I in F, right? xij dij. Is that correct? Is this the optimization function? Then, and what are the constraints on yi's? Yi's are element of 0, 1 because they are integral. And what is the meaning of this? Like for every j in C, you want to assign something, no? So what is that?
Every client we want one.
Huh?
For every client I we want one xij to be one.
Okay.
Combination of
What is partition? Please look and say what do you mean by partition?
so this xij can take a value 0 or 1. That is either a parent is
Okay. So fine. So I also have xij is element of 0 comma 1. Then what?
so each client should be assigned to at least exactly one facility.
So how do I put that as a constraint? So for every j in customer, summation I in F xij is exactly equal to 1. Okay, fine. But like, is this over? Is it okay? Is this enough, sufficient, is my question. Tanmay, is it sufficient?
No.
Okay, excellent.
Interconstraint.
Y and xij have to retry yi.
Exactly. So why it is not sufficient? I mean, yeah, I mean this xij and these yi's has absolutely no relation, right? Okay, fine. So all I care about is, for example, look at this. What can happen? Okay. So what I can do,
Also can ensure the metric
huh?
metric
What is metric constraint?
at the time.
That's a property of distance function, right? That's already there. What do you mean by I have to ensure that it satisfies? I have given some bunch of numbers that they satisfy some property among themselves. What I mean that I should ensure that they are okay. So for example, the problem is that maybe some set of facilities are open, okay, but Xij's, like, so this is the set of facilities that I decide to open, but these Xij's are one for some different facility. So like, what are the solution? I have, because they had no relation between them, I mean, all I care that from each of them Xij should be 1. So let's do one thing. Let's just open up one facility, right? And okay, and what is this? Xij times d times I times j. Okay, so this is also there, right? So what I'm saying to you that there could be a possibility that, so for each x1, let's do one thing, okay? Let's for each x1, okay, I look at the facility which is closest to it, okay? Look at the facility that is closest to it, and let's assign xij equal to 1 for that closest facility. Imagine that I have customers 1 to clients 1 to m. For each client j, I look at the facility which is closest, facility that is closest, okay, say I. What I am going to do, I am going to set xij equal to 1, that's it, because anyway these are separate variable assigned to each of this. I did this, right? Okay.
Meaning for every yi that is set to 1, you assign that say yj is set to 1, then you correspondingly set an xij to 1 where I is the closest.
What do you mean? Look, I fix up a client, say j,
Yes.
and now from j, I know all the facilities, right?
Yeah,
I know the distance. I look at the facility which is closest to me. I set the corresponding variable to 1 and rest to 0. Okay. I mean, for this client, this is the best he can hope for. Still, these constraints are satisfied, and all y's I set to 0. I set to 0. See, this is a feasible solution to this. No. All yi is set to 0 and some xij's are set to 1. Come on, here's an LP and I have given you solutions. Is it feasible or not feasible? That's all that I'm asking, right? For each client, this is exactly equal to 1 because I I went and one variable I set 1, rest to 0. This is fine. Xij's are between 0 and 1. Yi is between 0 and 1. And of course, this is the best function you can think of because you have to set at least one guy is 1. If you set this one guy 1, then this guy, this. So for a particular guy, this is the minimum. So if I don't set, here is the best cost function that I could come up with, which satisfies all this, right? Because in this does not contribute. This has to contribute some dij times, because you have put it equal to 1. So I have to set one guy to 1. So which one should I set? Among all these numbers, I set the one which is the minimum. I mean, every client must pay at least the minimum to one of the facility, but like it has nothing. I open 0 first. So all I'm trying to tell you, a feasible solution to this LP has absolutely no bearing on our problem at all. So this is not something which means anything to the problem.
When this working, xij is equal to 1, then y of I is equal to 1.
So what should we say? So what we will say we'll just add an extra constraint, and I'm going to say that for all I and j, yi minus xij is greater than equal to, yeah, that's it. One second. Hello? Okay. So this is all that I am going to set to. Okay. But now notice what happens. Okay. If you set some, yes?
We need this constraint, or if we just write summation of xij is less than equal to yi.
I also want to ensure to you that if you have set some xij's to 1, corresponding guy has been set to 1. You understand my point, Pallavi? So what is my, so if you do just a sum thing, I cannot guarantee this. So to guarantee this, I must ensure that if if a customer is served by some facility, then that facility is open. Right?
If we do summation xij is less than equal to yi,
Summation xyj
xij is equal to or less than equal to yi.
is less than equal to yi. This one? No. Look, so but look at this. What does this means, Pallavi? What is like yi is greater than what does this means? Like wait, is
0.
what is xij?
Customers assigned to facility I. Xij 1 meaning j customer j.
Look, imagine yourself, Pallavi. Can this be less than equal to 1? Imagine that I have assigned 10 people to customer yi. Right?
Oh, yeah.
Left hand side is 10. Right hand side is 1. I do not want to pay 10 times, no? Because I only open facility once.
Right.
Okay? There is no minimum number of facility, no? Is there any minimum cardinality of facility? No, I have never said minimize. Oh. Minimize the cost function, whose cost is. So like I'm saying this is a minimization function. Our goal is to just minimize cost of x. Okay? So this is my ILP or whatever you want to call it. Okay? And now notice that if you give me a feasible solution here, I can map it to a feasible solution here. Okay? How I can map it to a feasible solution here? Okay. So look at the set of guys which are assigned 1. Right? Look at the guys which are assigned 1. Now you know that xij is, so he has been assigned to exactly 1 guy. Right? Okay. And for all ij, yi minus xij is greater than equal to 0. It means the guy who he is assigned to, that must have been 1. Right? So that guy exists in my object. So that is this, this is this. So if you give me the best solution, integral solution, then that definitely is a feasible solution. Now if I allow you anything here, what do you call, more than this. So what will be an LP solution? Okay. So if I have to write, so this was kind of integral solution. If I have to write an LP solution, all I care about is the following, right? So the cost function is this. So for LP, what will, I want to minimize this, right? But rather than saying that, look, we had this extra constraint, right? That for each client j, look at I in F, xij was exactly equal to 1. I relax it and say it is at least 1. Okay. So this was one constraint. Okay. And then I also say xij is greater than equal to 0, yi is greater than equal to 0, okay, and I leave this constraint for all I and for all j. Right? This basically tells us that if you have set this to 1, then the corresponding guy should be set to 1. That's all that it means, right? So if you have partially assigned, so now think of this way, this is like a partial assignment. In the sense, now for a facility, it's like I can 30% be assigned to facility 1, 50% be assigned to facility 2. But if you have been assigned 30% and 50% and 80%, then the corresponding 30%, 50%, 80% of those facilities should also be open. Right? This is exactly what it means. Okay? So this is my LP and I'm going to solve it. I'm going to do no tamasa, I'm just going to solve it. That's it. Okay? Okay. Okay. So it's a minimization problem. So this provides a lower bound on the cost of ILP. Right? Is that fine? Okay. So let's solve this. So what I'm going to do is that I'm going to solve, okay, so let x, y be a fractional optimum solution to the corresponding LP. Is that fine? Okay. So basically, now I have solved it, I have got it. Okay. So let's look at for each j in client. So there are two things. One, certain amount of money or certain amount of value facilities pays to this LP, and certain values each client pays to the value. So what I'm going to say, for each j, let's say what is the cost a j pays. So a cost a client j pays, cost is summation over that quantity he pays, right? I in f, what is that? Xij, right? And distance from I to j. This is what a client j pays to this cost function, right? Because it is sum over each client and this quantity, which I'm going to call it Cj. So what I want, so what is my goal? Given xy, I have to come up with some sort of, basically with the help of xy, I have to come up with what? Some x subset of f such that cost of x is not too bad with respect to LP value, right? This is what I'm saying, that cost of x is some alpha times my LP value, at most alpha times LP value, and cost of x is at least LP value. So this is, we'll get that alpha times approximation algorithm. Okay. So with the help of xy, this. So what is my goal? I do not want any customer to pay too much more than this quantity. You understand my point? I do not want any customer to pay too much more than what he is paying in the LP. So that's my goal. Okay. So suppose, so I find cost of x, if I give me some x subset of f, I know how to define cost of x, right? This is like, once I give you a set x, oh, these are the where I'm going to open my facility, cost of x is extremely well defined. Like there's extreme, so I'm saying with the help of my xy, I'm going to define what is some, I'm saying, okay, actually with help of this, I'm going to tell you that please open your facility on this set x. That's all that I'm saying. Okay. So now if I told you this, then what I know? So I know, so if I'm going to show to you, cost of x is less than equal to, this is LP value, and this is some alpha times LP value, which will imply this is a alpha approximation factor. Is that fine, right? So with the help of my fractional solution, I'm going to make a decision that I'm going to open here, and I'm also going to show that cost of opening this is not more than LP values of this. Okay. So like this is my hypothetical x that I want to, I do not know yet, which I want to construct. So suppose this is my x, right? I said, look, I actually don't want to pay too much, like, so, and suppose this is my facility that I have opened, think of this, and here is your customers, and they have been assigned to closest this thing. I'm saying that this payment that I am doing, so I was paying to my LP how much? CJ. And I want to say that, look, me, I'm okay to pay CJ times some fraction, like maybe I'm paying CJ, if I'm paying some 35 times more than CJ, then total cost of customer is not more than 35 times this value, which is fine, right? So I'm saying I do not want to pay too much more than how much I am paying here, and that too much more is something which the algorithm decides to quantify as you make progress. Okay. So to do that, I say I am fine. So customer J says I pay CJ in LP, but I am willing to pay, how much I am willing to pay? I am willing to pay rho times CJ. Rho is some greater than equal to 1. We will fix that. Okay? I am willing to pay. Okay? So you fix this variable. I am saying, okay, I am willing to pay this much. Okay. Okay, that's great. If he is willing to pay this much, then let's see what all facilities is accessible to him and what all facilities is not accessible to him. Okay? Okay. So now let's define the notion of accessible facilities. Okay. So think about it. Okay. So what do you think are potential accessible facilities? Okay. Look, I mean, it's, think about it. When it comes to X, he has to pay some distance, right? And I'm saying, I'm not willing to pay more than this. So which facility is accessible to him? Whose distance is less than this one number. I'm saying to, because in real solution, I'm going to pay Dij, some. But I'm saying, but there could be some facility which I have to pay much, much more than this quantity. I'm not allowed to pay that because I'm only allowed to pay, I'm only happy to pay only this much. And every customer pays Dij, where J is the closest customer in the set X, right? Okay, so I'm going to define, okay. So for J customer, let's write down which facilities are accessible to him. Only those facilities are accessible to him for whom Dij is less than equal to rho times Cj. Right? Because only then he will pay. I said, aha, in my solution you paid Dij, but now if I can assign every guy, so imagine yourself that now I'm able to assign, I'm able to find a set X such that X intersection Nj rho X is not equal to empty for all J in customer. Then what I have done? Then for every customer, I have assigned, like, so for X intersection Nj rho is empty, it means the cheapest customer can only pay less than this. It cannot pay more than this, which implies that at least this part of contribution of these customer is not more than factor rho times whatever it is. You understand my point? Okay. So that is my goal. Okay. So these are my accessible facilities. Okay. And here I have not fixed rho. Right? I have not fixed rho. Okay. So this would be a very ideal goal, but even if we don't achieve this ideal goal, if we can say little bit okay, then also I'm fine, because then that little bit will be charged here. So that's fine. Okay. Okay. So observation 1, notice. There could be some j, some I in my facility such that xij is greater than 0, but j does not, I does not belongs to my, right? There could be some, my LP gives him some value, right? But it's like, okay, so what does LP tells me? That you are like 30% assigned to this facility, 50%, maybe 1/1000% you are assigned to some facility. It's possible greater than 0, but if the distance is really too much, I'm not going to put him here, right? So it's possible that fractional guy assigns me to someone fractionally, but it may not belong to this. So this is something to observe, right? This is what I'm saying, because I define this definition without looking at my XP. I said, okay, but I need to relate them. But it's possible that when I solve LP, there is some facility for which corresponding Xij is strictly greater than 0, but it is not part of my accessible facilities. Okay. Okay. Next, what I do? So I want to. So given xy, move to some x hat y hat, and cost not too bad, and that respects accessibility. You will understand what I mean by accessibility. It means, what it will mean, that actually in x hat, for those j which does not belong here, I will assign 0. It means those do not contribute to this, okay? And it will not be too much, don't worry. How do I do this? Okay, so basically we are massaging this solution. Okay, we are massaging this solution to get to x hat and y hat. Okay. Okay, and how do we do this? So let me define this massage solution. So massage solution is, what is y I hat? I have still not fixed what my rho is. Okay, but I know rho is greater than or equal to 1. Maybe let's say strictly greater than or equal to 1. Okay, because okay. Okay. So it is, I have slightly increased the value. It's like tong. Okay? Okay. And now I have to also define xij, no? What is xij hat? What do you think xij hat I will be? I said, okay, if I belongs to my accessible, right? J is a client, nj rho, I will assign something. Else, what will I assign? 0. Okay. If you do not belong to this, go away. Okay. And here also I will assign rho minus 1 xij. Okay. Is that fine? But notice, first of all, we have to show that x hat y hat is a feasible solution to this. That's one thing I must show. And secondly, for now moment, what is the value of LP? It just increased by factor rho by rho minus 1. Why? Because everywhere I just multiplied with if x hat y hat, so I have just, because either you contribute 0, no problem, or I have multiplied you with some rho by rho minus 1 factor. So the total value of new feasible solution of this is not too larger than LP. It's basically rho time minus LP. Okay, that's it. Okay, so in other words, what I'm saying is, okay, so I have written this, you have written the LP. What can I rub? Oh, that will come. Okay, I mean that you like. Okay, if I fix rho, what is the smallest quantity should I do? I know what I wanted to do here. I do not want my this. So this is fixed to be 0. Now, what is the minimum number I should give such that this is feasible? given that I allow you rho to take, right? It means I'm allowing you to take more things. So what is the smallest quantity that I can, what is the smallest ratio that I can put it here such that this becomes feasible? That's it. So
When you wrote that row there, I thought row is the addition, the factor amount extra we will be paying.
yes, but that I mean, that's an idea. No, it's even more.
Sorry, row, yeah.
So I'm like, so rho is what I'm willing to pay. Okay. So let's see first of all why. So first of all, let's look at that this does satisfy all the feasible constraints. So let's call it LP hat. So what we know, I have LP and I have LP hat. So we know that LP hat is rho by rho minus 1 times LP. This is very clear, right? Because every value is just popped up by rho by rho minus 1. So you can just take this rho minus 1 common from everything, you will get that. Okay? Okay, fine. But what about feasibility? Okay, what about feasibility? It may not be necessarily satisfy this equation. So for example, first let's see, is this done? Okay, this is done. Why? Because what I have to show, for all I, for all j, yi hat minus xij hat is greater than or equal to 0. Right? If I substituted xij hat to be 0, I don't care, because anyway this is 0. But if every yi hat has been assigned how much? Rho times rho minus 1 of yi, and what is xij in this case is also rho minus 1 xij, which is equal to rho minus 1 yi minus xij, and this is greater than or equal to 0, right? So this is greater than or equal to 0. Right? Because this is not a 0 quantity. So if this is greater than 0, then this is greater than 0. That's it. Is that okay? No? Okay. So look at the other thing. Now I have to worry about this constraint, which is slightly more tricky to show. This is not obvious. This is not obvious that whatever we did, oh, this is true. Why? Because for lots and lots of facilities, you might have substituted 0, right? And those were contributing to get it greater than or equal to 1. So how do you know that for those facilities, you have added enough previously that does, right? Okay. So now, what is Cj? The value Cj is this quantity. Let's write it down. I in my facility, xij, right? So now I make a slight change. I say I in nj of rho dij plus summation I naught in nj rho xij dij. Is that correct? Because it is over all the facilities. So those facilities that belongs to my accessible first and those which are not. That's it, just exactly the sum. What can I say about this quantity? Let's try to understand this. What can I say about that quantity? What? Yeah, this is 0. We know that, right? In the x hat, so if I would have substituted xij hat, this will contribute to 0. That's okay, right? So we know, okay. So, but we also know something about dij. It is strictly more than rho times Cj. Okay, strictly more than rho times Cj. So first of all, my claim is that let's call it B. B is at least, let me see, it should be at least 1 by rho times Cj. No, less than 1 by rho times Cj. Why? Okay. B is at least this much. Why? Okay. look at this quantity, right? Summation xij dij. What is the dij property? It's strictly greater than rho times cj. So this is summation xij rho right? Right? So this quantity is this, and this quantity is less than equal to Cj, because Cj is equal to everything. So Cj is at least this quantity, which is rho times this, right? So what is the meaning of this? This quantity is at least 1 over rho. The value of this is less than equal to, so not dij, this summation of xij is less than equal to 1 by rho. Is that fine? Okay. So now, so what did we learn from there? That hey, this is where the rho minus 1 comes. Why? Because I have set some of the people to 0, but their contribution to xij is very minimal. It is at most 1 over rho. So I need to move that to 1 by rho, more than 1 by rho. So I popped up everything which is not there by more than that. You understand my point? Okay. So what I mean by this, let's try to understand this. Okay. Imagine yourself that you have some numbers, 5 numbers here, and some 3 numbers here, which is equal to 1. And I told you that this number is less than equal to 1/3. Then how much should you multiply this so that it becomes more than 1? Yeah, but so what is that number if I want to fractionally define everything to? So that will be like, that is exactly what it is rho minus 1 is. Right? So that is how the quantity which I multiply comes from. That if, so basically what it tells us that, look, this is equal to 1. So if some distance is too far away from me, some facility which is too far away from me, then the corresponding xi should be too little.
Yeah, the LP will ensure that.
Yeah, so that's exactly. So now, what I am not including in this facility, those facilities which are too far away from me in the terms of rho. It means the values of those xij will be too little, right? Because otherwise they cannot be equal to 1, right? So further you go, lesser the weight xij will give, because for the fractional solution, if it pays more to that distance, that will come in the cost function, no? So he doesn't want to pay that much, right? So far you go, the little portion from here he can take, right? And that is what I'm trying to quantify here. So now is it clear why rho, like once I decided rho by rho minus 1 is a mathematical manipulation that comes from saying, okay, what is the smallest quantity should I take such that I can make sure that this inequality holds. Okay? Okay. Okay. So now let's try to see. So we know that this quantity is at most 1 over rho, right? Which implies that summation I in ng of rho is how much? Xij dij is at least 1 minus 1 by rho. That's it. Because if this quantity is strictly less than 1 by rho, then this quantity is at least 1 minus 1 by rho, because this was at least equal to 1. Is this fine? No, what am I writing? This quantity is at least. Yeah, sorry, that was my mistake. Is that fine? Because what was the constraint? That summation xij is greater than or equal to 1. Check. Okay, so among some of those values is 1 by rho, so the remaining value is 1 minus 1 by rho. Okay. Okay. No, please read, no? Look at the constraint.
Yes, in constant it is not there. So
This is just a proof. Proof told us that, what did I show? I showed to you using proof that this quantity, this implies summation xij, okay, I not in nj row is less than equal to 1 by rho. Cj will get cancelled, 1 by rho. Okay. So this is at least 1 by 1 minus rho, which is equal to rho minus 1 by rho, right? So now if I multiply each quantity by rho minus 1, this will become 1, and that is why I have rho minus 1. Okay. So now this is equal to like this is this much. So summation xij hat here is nothing but rho minus 1. So if I do this, this is nothing but xij hat is nothing but this is equal to summation rho minus 1 xij, right? And now we know this quantity is rho minus 1 times rho minus 1 by rho got cancelled, equal to. That's it. Okay. So what I have shown to you is that it is indeed a feasible solution, right? So this is so I started with an LP, I have come up with a feasible solution, and now I have to do something more. Okay? Okay. So now I will do the clustering steps. Is that fine? Okay. So I will now from now onwards I will not work with this xy, I will work with x hat y hat whose value with respect to LP is rho by rho minus 1. Okay? Okay. Okay. So now notice, okay. So what does x, okay. So what is the massage solution tells us? Massage solution tells us that given this x hat, y hat, this is my massage solution, right? This is my massage solution. So if everybody, so now it tells us the massage solution, and what is a good property of the massage solution? The massage solution good property is that, yes, it means for every client j, for all I, for each client j, for all I, xij hat is greater than equal to 0 if an like implies j belongs to nj of rho, right? If it is greater than 0, then this is definitely true, right? I mean, that's all. Okay. So and LP hat is less than equal to rho by rho minus LP. Okay. So this is great, but still, what is my job? My job is to find an x so that every assignment can happen. Like, so that assignment can happen. Like, I have still not told you x, right? I have told you that I would like to, for every client, I would like to put him here. That's all that I have told you. Right? Why? Because it makes sense to me, because other distances are too far that I do not want to pay too much more than this, is what it is. Okay. 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 Now I also have some beautiful properties of okay. So now this is what is called clustering step. Okay. I want to cluster. Okay. I want to cluster. So how do I want to cluster is the following. Okay. Now what I do is the following. Now you, in the beginning I have not assigned any what do you call, any client. I have not assigned any client. Okay. So let's say U denotes unassigned client. Okay. Like, right, in the beginning you will see, but like when not recursively, when iteratively we will try to build assignment, some people would be already assigned. Okay. So to do that, I will do something. How am I going to consider these clients? Okay. So I'm going to consider these clients. So I sort the clients. based on how many clients we had? M clients, right? What is the meaning of this? Do you remember? I had defined Cj. Cj is this quantity, right? So, which is the client whose cost, distance, whatever that with respect to xi is minimum to this, and this is how I have assigned. That's it. This is just a gridly, and we are going to follow the process in this process. Oh, yeah, this is right, right? So the client which contributes the most will be assigned at the last. Okay, so we are going to follow this methodology. Is that fine? Okay, and now what could be the most greedy way of doing would have been that for every client I assign someone here. That's like that problem could be that you might open up too many facilities. We have still not cared about one thing, right? So if you look at the cost function of our LP, cost function, how is the cost function? The cost function, if you remember, is given by yi hat fi, because we are only working with this, plus summation over what we wrote, I in facility, j in client, I in facility, distance ij, xij hat, right? This is what we know. Okay, and is that fine? So this is what. So now we will try to focus on this part and try to see how much can we do. Okay. So what we are going to do is the following. Okay. So suppose at some point of time, so I'm going to tell that suppose some client j has come now, which has not been assigned. Okay. Some client j has come which has not been yet assigned. Okay. And this is, so among all the client that is uncovered, what is the property? That Cj is the smallest among the rest, right? This cost is the smallest among the rest. So like, because we are following in this order. At this point of time, okay, what facility should he be assigned to which can be good for him? What facility should he be assigned to so that it is good for him? I mean, if I am looking for a good approximation, then I can assign fj to, like, look at the facility that he assigned is to all those I, right? And such that all those I know xij hat is greater than equal to 0. This is, I mean, this is the ideal thing, but this is exactly equal to what? This is what it is.
There might be multiple facilities which are within row distance.
Sushmita, but those all were part of no n row j, no?
Yeah, accessible.
Yeah, but this is exactly equal. What is it?
Yeah,
All those
by
facilities.
definition, xij hat is
Okay.
greater than 0 means they are
Okay.
accessible.
So this is not a surprise because this is exactly what we wanted, and we are very happy about it. That this is exactly what I. But like, what about other facilities? So, but now imagine that these are the facilities that when J came, these are the facilities you are thinking of. Okay, right? These are the facilities you are thinking of. But there could be a conflict in the sense that, look at the facilities here, for which all client, this set of facilities could be good. Think about it. For which set of clients these facilities could be good? Imagine any other facility. Look, these are some set of facilities, right? So suppose I have a client J, suppose I have another client J1, whose intersection is this. That's great for him, no? Because, or maybe there is some other which intersects with this facility. That's great for him, no? Why? Because, I mean, he is telling me, boss, you open up any of these facilities, I will be very happy. So, in particular, if you open among this also, I still be very happy. Everybody has a happiness ball. And what was that happiness ball? This N rojo, right? So, I am saying, if my happiness ball intersects with your happiness ball, I am fine. Like, I give up. If you are able to assign one of these objects, I will be very happy, right? So, okay. So, what will I do after this? I said, any unassigned client whose ball intersects, throw him out. He has been served. You understand? So, so now, what does this tells us also? This tells us that, so now let's call J being representative, okay? Why? Because J created the ball. J created Fj. So, I am going to call J is representative, okay? And what I am going to call, it causes, when J came, it created. I am very happy with any of these things, okay? Any other customer whose N row J or corresponding Xij hat intersect, whose accessible facility intersect, okay, claim that customer to be served. Is that fine? Okay. And I am done. Okay. So, by looking at all this, what are the properties do we have? Let us notice. Can I rub this? Yes.
Here in this other happiness balls, I can assign it to someone which is not in that happiness ball.
Meaning?
We delete that customer from
What?
the intersection of that ball with someone is some non-empty set.
Yes.
But it's not necessary that after if I delete that person,
That customer?
I don't assign any one of them.
Meaning? Oh, you want that? Why am I not assigning one? I have not even told you whom I am assigning yet. I have not told you how to get your set X. Not yet. I am just giving you process that.
Some people can be.
Let me draw.
simultaneous,
What?
you know.
So I can see that Fj is a subset of Nj row by the construction of X hat.
Hmm.
Why is Fj equal to Nj?
Okay.
Subsets
Doesn't
good
matter.
enough, right? All you need is that you have given accessibility.
I mean, I don't think that would have been. Okay, fine.
So are you saying, Saket, with this
Wait.
that there are multiple?
No, wait. So you were saying something, Sobir.
Sir, I was saying that
Tell me.
sir, if those balls are there and I delete some of the
Customers.
then how will we ensure that those customers are served by any of those in rows?
I will. Let's look at it. How will I? I have not yet decided which is your X is. Did I tell you what X's are? I am just giving you some process, right? I am giving you some evolution process of doing something, right? I have not even I have not told you what X is, right? Okay. But let's look at the process. What happens? First client comes. He makes his ball, okay, and he says, "Hey, these are important object," And which all customers did I delete after this? I deleted every customers whose ball intersected with this. Okay? I deleted all these customers. I call them served. This is the first iteration. Next time, when a guy comes, okay, who is among all this, he creates his ball. Notice that set of facilities here and set of facilities here do not intersect. Because if it intersected with this, then it would have been thrown. That's right? Okay. Huh? Right. So let's call J being representative. So I'm going to denote R is set of representative. Okay. And Fj is a set of facilities where Xij is greater than or equal to 0 at that. And there will be some set of facility which is Xij is greater than or equal to 0 because this is equal to 1. So there are some facilities. Okay. For set of representative, notice if J1, J2 is in R, 1 second, is the representative. First then I claim that Fj1 intersection Fj2 is empty. That's the first thing.
Are you saying that the approximation is correct?
I am not saying anything yet. I am not saying anything at all. I am just explaining the process, right? And I will tell you why am I doing this in a minute. Give me a minute now. I am not claiming anything. I have no idea. This is so basically. So next again I did the same thing. I mean this guy could be the guy who comes here. Everyone could be intersecting with his green balls, but this guy will not be intersecting with the red ball. That's all that I care, right? It could be like this. I mean, I'm not denying it. That's it. Okay. So this is how the world looks like after the process, right?
One of the green balls could intersect more than one red ball.
Yeah, that's you're right.
No.
But then that client would have been thrown from him only, no? Like so these are the I'm not saying that balls do not intersect. I'm saying that they are the clients. Wait, they are the clients which are thrown because of creation of this red ball. Okay, these are customers thrown by creation of, let's say this is J1 and this is J2, creation of Fj2. Clearly those guys will not be intersecting any previous one. I'm not saying that this is not possible. Look, this is very well possible. This is very much possible. But he was thrown already before. Like first time when you come, you are thrown away. Okay, that's my end of the process. Okay, so this is my end of the process. What do you think? Okay, so now let's look at this. I still have not made X, right? I have still not made X. Okay, so let's make X now. Okay, so how will I make X? It's very easy now. Okay, so why it is called clustering? Because look at the red balls, they are disjoint. Okay, so every red ball, let's create these red balls. They are disjoint, and they have their representative. Okay, so let's call the representative J1, J2, JQ. So there are Q balls. So they have their representative. No, my X is created as follows. What is my X? For J1, find the closest guy in F1, right? So what is this? I take the facility J, X consists of J, where, or rather, okay, I should have, this is customer, right? No, for each customer, I make these balls, right? IQ, right? So what is this? Let's call it, it consists of, it's so ugly notation, JI1, JIL, where JIL is the closest facility in F of this is wrong. No. Like I was right. My notation was correct. Like I made my mess of my notation. So J1, J2, JQ. So what it is? It should be I of JL, where I of JL is the closest facility in F of JL, where IJL is the closest facility in FJL to whom? To JL. Right? So this is what this is my X. Okay? This is the creation of my.
So how did you create the first red ball?
What do you mean by first red ball? I got the first guy.
Which after ordering the cost.
Yeah, I say hey.
But the costs are that CJ thing that you had defined before. That was with respect to the optimum LP.
Optimum?
LP.
Yeah.
So you solve the LP, sort the CJs.
Yeah.
And each time you process that. But how do you? What is the red ball consist?
Red ball consists of this is a definition, no? All those I such that X.
Accessible location.
No, I'm saying look at the corresponding Xij hat value, which is greater than or equal to 0. That's it. And that is consists of n row j because of my construction. Anything which was outside, I put it to 0 anyway. That's it. And this is my end of my construction. What is not clear to us? Yes, Tanmay?
Should we not choose it to be the cheapest facility in that sense?
Okay, let's see. You are right. I shouldn't be choosing because you are right. Because anyway, everybody is close to each other. Wait. No. I shouldn't be doing this. This is right. Okay. He's right because everybody is anyway close to him. He's allowed. So I should not care about closure. What should I? Because among all them, he's right. I should Xijl. IJL is the cheapest facility. You are right, Tanmay. This makes more sense. Let's see if I can manage to prove this. Is the cheapest facility in RJL. Opening cost. Okay, with risk because and why it makes sense? Think about it. All these guys are equally good for me. So if they are equally good for me, then let me choose the one whose opening is the smallest amount. So this is like better greedy choice. Because why were we making these balls? They're making balls that these are equally good for me.
Yes, but there is a contribution of this in the whole cost.
Yeah, let's.
Somehow you are being greedy in the left sum.
I'm already greedy being in the right sum when I made my clustering.
Yes.
Okay, so.
Could also pick a facility that falls in the intersection of multiple green balls.
I mean, I don't know how to handle them. That is too much of a. I mean, I don't know whether that strategy will work or not. Yeah, I mean. Okay, I have yet not used the fact. Okay, so let's try to understand that at least by doing this, we didn't pay too much here at least because let's at least see that. Okay, so let's see. Okay, so let's fix J in my customer list. Okay, there are two kinds of people. J is my representative. How much did I pay for him? If J is in the representative, how much did I pay for him? Huh? What? If J was representative, I paid Cj. Did I pay Cj if I was the representative? Please look, no. Please look.
Starting cost.
Like, not for, if, what was the definition of Fj? It was in some nj row. So how much I could have paid?
Row times the CJ.
So did I pay Cj or did I pay row times Cj? So for each of this, I paid here row times Cj. Okay, because they were in the ball. Okay. So now the most interesting case is when J does not belong to R. Why J was not belong to R? Because someone knocked him out. So let's see who knocked him out. So some J1 knocked him out. Why he knocked him out? Because okay, no, let's be at least nice to the audience. Okay. Okay. So this is the ball of J1. Okay. Okay. So this is the ball of J1. Okay. So ball of J1 is nothing but, so let's draw J1 here because this is just set of facilities, and J is outside, and this is why, because if I look at the green ball for corresponding to J, it was intersecting this. This is the right. Okay. Excellent. So there is someone here, some facilities here. Okay. And you chose someone here, right? So we chose some I, J, something. So suppose the guy which was chosen is this, completely outside for all that you care. Okay. So I want to know the distance from where to where, here to here. Like this is what I'm interested in, to know that, because this is what, like, because because our assignment assigns the minimum. So if this itself is bounded, the function J that will assign minimum can only be better than this. If I can show the J to this guy itself is small. Okay. Is that fine? So how can I reach there? You tell me. What is the way to reach here? Right? So how should I apply triangle inequality? I want to go from here, so I first go from here to here. Right? I first go from here to,
In the intersection there can be multiple.
yeah, so I just,
So which one?
any one of them, pick. But I know that I can go from here without paying too much. Okay. Now where do I go? I can go from here to here. Okay. Okay. And then from is this, which one? I wanted to go here, right? No, and then from here to here. This is how I will go. And I know because of triangular inequality, this distance is smaller than these three black distances, right? Okay, excellent. What is this distance? It's in the green ball. So what is this distance? Rho Cj. Excellent. Very good. Rho Cj. Okay. What is this distance? Rho Cj1. Right? Happy, happy? Excellent. Rho Cj1. And what is this distance? Rho Cj1. And what is Cj1? Is less than equal to Cj. Okay. So how much did distance I paid? We paid, let's look at this. So this distance is at most rho Cj plus rho Cj1 plus rho Cj2 is, sorry, Cj1. So can I say this 3 times rho times Cj1, Cj. That's it. So at least all these guys are not paying more than 3 rho. Each of these guys, whatever is the best here I could have hoped for, I am not paying more than 3 rho. That's right? Okay. So this is great. Now let's worry about this. I think I'm doing a great job. Not that I, okay? Okay, so now I would worry a little bit. I would worry a little bit about the facility locations. Okay. 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 So let's prove some beautiful property. What happened? Look at the facilities here. Okay. They have some beautiful properties. What is the property? What I'm going to claim to you is that, okay, that if you take J in representative, okay, and then you do summation over I in yi is at least 1. Hat, of course. This is greater than equal to 1. Do you see why? So what is our key observation? Look at the ball Fj. What is it? So let me rewrite the definition of Fj. I said Fj consists of all those facilities I such that xij hat is greater than 0. So from here, everyone. But what I know about this? I know about this that summation over I in Fj, xij hat is greater than equal to 1. Right? Because I mean, others are 0, so they don't matter anyway, right? Because if you look at the inequality, it says summation over all the facilities xij hats is greater than equal to But those guys which are not 0, they don't contribute. And this is also here we use the fact that Fj hats are disjoint because why? Because so all the variables that assigns non-zero to this is there in my Fj. You understand? All those guys with whom he is non-zero is there, because if anyone would have been non-zero with the previous guy, I would have thrown him out. So this inequality holds. Can you? And what else do I know?
What's the role of the representative here?
Huh?
What is the role of the representative here?
Representative tells that I created the ball.
No, in this thing.
No, because I'm only saying claim, because look, you are only opening a facilities corresponding to representative, right?
Yes.
That's it. So I'm trying to understand how the xij costs and why I relate it. They are also related, no? So okay. So what do you know from here? What do you know from here? This implies that yi hat I also know is greater than equal to xij hat. Okay, so if I sum over this I will get it, no? Look, I also had this yi hat minus xij hat is greater than equal to 0 for each I, which implies this. Now, if I sum them up, then I get left hand side, and right hand side I get this, which is at least 1, which is, so this is at least 1. Done. How did I create FJ?
So for every client,
No, not for every client. I had a process. I created a ball. What is the definition of ball at this point of time? The definition of ball for any vertex is all those variables which are non-zero to him. This is why I massaged, no? Right? So I created a ball, and any guy who had a non-zero variable here, I deleted them. That's it. So when a new guy comes, he's not interested. His xij values are not assigned to any other facility. Like those are not even considered. This is why it is called clustering, right? These are clustering, right? Look at the facilities here, right? These facilities which are assigned non-zero to this, look at this guy. They do not intersect with J2 because if they would have been intersecting here, I would have thrown him out. That was the process. So when I'm considering all the facilities which is assigned non-zero to him is there in Fj. That's all.
Okay. So I look at Fj and then from Fj I pick up the facility that has cheapest starting cost.
That's right.
That's the one I open.
Hmm.
And after this, I basically delete all those clients.
No. No. This is at the end. What do you mean by client? I was deleting all these when I was creating these red balls.
Okay. All right. So we can't do this in.
No, why should I do it? I mean, I'm telling you my process. No?
All right. So okay. So the thing is between, if I look at the balls that are the people who are being served by the second ball and the first ball, let's say,
They are distinct.
they are disjoint. Yes. This argument here, this one assumes that okay, J1 was being served by somebody who's between distance rows CJ1, right? This diagram.
Which diagram are you
This
talking?
one, J1 comes before J, right?
Yes.
Cost of J1 is less, so J1 comes before J.
I don't know who. Look, there's a notion of serving. Serving is very simple. I told you X,
Yeah.
define cost of X. That's it. But I'm telling you that the cost of X is not too large. Why? Because a client is assigned to facility which is cheapest. And I'm telling you, actually, I have at least one facility to my client which is not too costly. So if you're assigning a facility which is closest, that cannot be too bad.
Where are we using that assigning this thing?
Arey, Sushmita, come on. What is the definition of I told you X? Once I told you X, there's a canonical way of defining these things, right?
Oh, okay, fine. No, I'm just saying this thing, right? So, suppose J1,
J1, I'm not telling, there's no notion of throw. Look,
the client,
J1 was thrown out because of this ball. That's all that I'm using.
no, J was thrown out because J1 comes in,
Okay, so J has been thrown out because of
J1.
J1, yes.
Now, which facility you would open from J1's FJ1?
Suppose suppose I opened this facility.
Right.
This is the facility I opened.
Now think about all those elements like J who
Yeah.
are actually thrown out because they're.
Yeah, so pick up any J, no? So I want to reach here.
Yeah.
So to reach here, I can reach to a person in my ball because my ball intersects.
Yes, but that facility was not open. But the
Doesn't
distance
matter.
Exists. Yeah, distance exists, right?
Because I'm doing metric.
Yeah.
From here, this facility, I can go to the J1. From J1, I can get to that facility. So this much payment, this much payment, this much payment, I pay this much only.
So basically, people who were thrown out because their balls intersected with some, they are at this is the
Exactly.
maximum distance.
They are possible.
They are this. But when we are paying for the opening cost, right?
I'm not yet done, no?
Okay.
I'm trying to analyze.
That.
So I'm saying, for this it is for this it is each of them are not paying more than 3 times row,
The
whatever that.
distance value, yeah.
And everybody was paying some great amount, like best was CJ, they're paying some 3 times row here, right? But now I want to say what happens to the facilities, right? I want to understand what happens to the facilities, right? Like, because what I did from each of these guys, and this is where I use the fact that actually the summation y I hat is at least 1 in these balls. So if I look at all these guys, the summation of y I hat is quite a lot. And that's good enough for our purpose. Okay. Okay. So let's try to understand what happens. What did you open here? What did you open here? Cheapest facilities. Am I right? Okay. Okay. So cheapest facility, say some I. What can I say about this? Okay. So if I do this, summation I in Fj, right? Let's write down summation I in Fj, Fi yi hat. Is that correct? Right? I want to understand this sum. I claim, what is this quantity? This quantity is at least, say, suppose we opened some f I hat here. Can I say this? F I hat summation y I hat. Can I say this? I in fj. Can I say this? Because this is the cheapest among these numbers, which is because this is at least 1. I have shown this. Okay. Why do I care about all those things? Are you see we are done? We are done. Why we are done? Look, what is this? This is summation yi hat fi. Okay, very good. Who paid for him? Who paid for him? Look at this set of facilities here. Look at this set of facilities here. And look at this set of facilities here. This is disjoint, this is disjoint, this is disjoint. So whoever here is, whoever you chose here is paid by this quantity. Whoever you chose here, that amount is paid by him. Whoever you chose here is paid by this amount. Okay. So how much we paid? We paid only this much point. We paid only this much for the facilities. So we paid, yes, I paid yi hat fi only. Okay. So with respect to my real LP, how much this is? Rho by rho minus of, let's call this in the real LP the contribution of facility, FLP. Is that right? This is what I contributed. Okay. I have still, because yi hat was like summation yi times fi, where yi was rho times rho I. So this is y. So, and how much did I contribute here? How much did I contribute here? But notice here I was doing with respect to old cost itself. I was not doing with the Cj hat when I was doing this greedy. Why? Because so I don't have to lose rho by factor. So what is this guy's contribution? Well, this guy's contribution is, okay, 3 times rho times, let's say, let's call this C alg CLP, like customer's introduction in the real LP, right? LP, right? So how much we are paying now? Notice, so the total amount of payment that we did in my new solution, cost of x is less than equal to, let's read, rho minus 1 times FLP plus 3 rho times CLP, right? And I have to show this is less than equal to some alpha times FLP plus CLP. That's it. So now we will, we should do some backtracking, right, to do this. That's it. In contribution of the sum. So I want to show this is because that is what the cost function is. So if I substitute rho equal to, if you do some maths, okay. So let's substitute rho equal to 4 by 3. Then what we get? If I substitute rho equal to 4 by 3, then what is this quantity? Okay. So if I substitute rho equal to 4 by 3, what will be this? Rho by rho minus 1 is 3, right? Is this correct? 4, right? Okay, excellent. So this is 4 times 4 LP, and how much is this? 4 times CLP. So this is a 4 times FLP plus CLP. So now I chose rho, which gives me the best approximation factor. That's it. So this is a factor 4 approximation. Okay. So is that fine? So let's do a recap and then we'll go. Okay. Okay. So, first solve LP, massage the LP, okay, without losing too much. Okay, that's the second thing we did. And third property was then we massaged. Why did we massage? We said the facilities which are too far away from a customer shouldn't be assigned to him. Okay, so that was the message, right? So I said, this is what I did. Okay, so client J contributes Cj to LP. I said, I'm happy being served by facility such that distance from I to J is not more than rho Cj. This was my definition. And so with this idea, we massaged in LP such that for each j, xij was greater than or equal to 0 implied that I belongs to this set. So that was the whole idea. Okay. So and now our whole objective was to find a subset X of facility such that each client is either assigned in its ball or an adjoining ball, whatever that meant. Okay, adjoining ball. Okay, this led to what is that called? With this idea, it led to what I call representative and clustering. Representative and clustering of what? Of facilities, right? We clustered this facility. I said, for this guy, this set of, and what is the meaning of clustering? Like they have some similar properties. So with respect to all the clients, with respect to representative and people that we threw away, this set of facilities are equally good. Like with respect to this is what the clustering achieved, right? They're approximately good for all the people, for the representative and the people I throw out. So that's okay. But what was happening at the same time is that what was happening that, and when I open the cheapest facility, so think of this way, right? What is the meaning that I will open up some facility? Is that some yi has been assigned at least one? So the way it was being done is that if you look at the set of facilities here, their yi's values should at least be 1, because ultimately I'm also assigning this to 1. So if the yi value is too little, it doesn't. It's like if yi value is at least 1, because if it is too little, then the payment is anyway less. No, so up to 1, I'm very happy, right? Now that allowed us to, but suppose if my payment was, so why I needed yi hat to, imagine I'm saying, look at this yi hat values, I'm going to choose one integrally, right? But imagine that yi hat value was like 1/3 or some such thing, right? The total summation of yi hat would have been 1/3, then my factor of approximation will just blow up, because in the LP I am paying some 1/3 times some cost, but here I am paying full cost. But if the summation of yi is equal to 1, then I am able to sum the cost. It's like, imagine 30% of this, 50% of this, 80% of this, 90% of this, right? Of this quantity, but I chose the minimum of all this quantity. So all this guy can sum up, but imagine that summation of yj would have been half. This could be possibility. Then I can only say that this is, everybody of here is paying not once. I need 2 times the cost to pay for the facility I open, because imagine yourself, right? Here I wrote, no, look at this. This is this. I wrote, this is up perfectly fine. But I wrote, if this would have been at least half, then what I would say? So this I paid 2 times this. No? If this would have been 1/100, then for this opening cost I pay, because this is what I pay in my LP by disjointness. So for this payment, as good as I can get. So it is advisable for us that the yi values of this is as close to 1 as it possible, because at least you have to one open anyway, right? But not all the time you're able to do so. So when I was clustering this, I was also keeping this in my head that, okay, I have taken care of the distance function, but yi values are also going on increasing because they must be chosen integrally. And this is where we use the fact that this xij's and yi's are related to each other. Remember, right? And that will happen. That will automatically happen if in any situation, anybody who is assigned non-zero to this, you just have to do the left sum and right sum. This will always happen. This is at least 1, because that is how you have set up everything. Yi minus xij is at least 0, but at least summation of xij is at least 1. So summation of yi is at least 1. So they are related to each other. Okay, right? So it says these facilities. So if you look at the bipartite graph, what I'm saying, this guy must open up one of these facilities. So fractionally, at least it should at least be 1. Otherwise, it makes no sense. Right? So I could have written summation yi greater than or equal to some, like I could have just forced also in this, but that would make life a little bit more harder. Okay? So this is what we did. So this is why we were doing whatever we were doing. And once we have done this, we paid for this, we paid for this, and we just found the right row that everything holds. So this is it. So this is an example of deterministic clustering. Similar kind of clustering a similar kind of LP rounding can also be done for K-median, which I will not do. And from tomorrow onward, I will move to randomized rounding.